hello. What a lovely gathering to be facing, and you're all very welcome on behalf of Churchill College, if not to Churchill College. Okay, I thought I could hear an echo. I thought it might be registering, but I'll try it this way. I'm Ken Siddle. I'm the Vice Master of the college, and I can't say whether I'd have been here anyway. I might have been, but I'm certainly here because Dame Athene Donald, the Master, has had to withdraw at short notice because of a domestic crisis. I can reveal that her husband fell down the stairs and is in a very bad way, but having had an operation is now recovering. So Athene is very sorry not to be at this occasion, which she'd very much like to be, but then her loss is my gain, and I'm very pleased indeed to be here instead. It's essentially an initiative of the Alumni Relations arm of the Development Office at Churchill College, although certainly attendance was never intended to be limited to Churchill alumni, and I know that many of you are alumni, but some of you are not. I was told by Sarah that there was a feeling we should have an event that didn't simply revolve around eating and drinking, and I can say that eating and drinking this evening is conspicuous by its absence. And this particular idea, I think, arose out of a conversation between the office and, I think, David in the first instance, and then it gathered some pace, and here we all are. I have to say, before I forget, that we should all feel very grateful to Sarah Fall and John Pennant, who are both here this evening, for their work in putting this show together. John also suggested that I might say a few words about the college. They will be few, because I don't want to keep you from the main event. The main thing to say is the college is in excellent heart. We achieved, well, we first of all thought it was our best ever performance in the University College League tables, and then some people from 1965, when we were a slightly smaller institution, weren't sure that they hadn't done better. But anyway, in modern times, if I can put it that way, we achieved what was conspicuously our best performance, and on a rising trajectory over the last several years, have hopes of doing even better in years to come. We're also in extraordinarily good shape financially, not such good shape that we would never turn down any more offers of help. And for instance, we will be opening our new court, Cowan Court, to students in October of next year for the start of the next academic year. And that will be a magnificent new building. In best Cambridge and Churchill tradition, it will be rectangular, but quite unusually, it will be timber framed and timber clad. And we're very glad to have been able to call it Cowan Court, because the porters were sure it was otherwise going to become known as Fort Apache. But anyway, that will be a great addition to the accommodation of the college, which will benefit both our students and our burgeoning conference business. Another record was broken, we just heard at College Council only yesterday, the highest number of undergraduate applications we've ever had, again, beating last year's record. So everything I can say about the college, quite honestly, is record-breaking and good, and we're in very good heart indeed. So without further ado, I should get on to what we're all here to hear about, ice sheets and climate change, past, present, and future. Clearly an extremely topical issue as a very concrete reflection of the global warming debate, and John pointed me towards just how topical it is, highlighting, I apologize for this in some respects, these are not the strongest scientific sources, but no less than the Daily Mail on Monday had a banner headline, "The entire West Antarctic ice sheet could collapse and raise global sea levels by 10 feet, claim researchers." Decades of warming can start an ice loss that continues for millennia. At current melting rates, the ice sheet will hit a critical point in 60 years. And it said last year, scientists claimed that glaciers in the Amundsen Sea of West Antarctica had reached a point of unstoppable retreat. Now a new study has added fresh urgency to the issue. The research published today in the Proceedings of the National Academy of Sciences, which I mentioned to you, has a citation impact factor of 10 in round figures. And the research used advanced climate model to study what will happen if these glaciers collapse. On the same day, the Daily Telegraph headlined, "NASA reveals that Antarctica is actually gaining more ice than it is losing." And went on to say that Antarctica's ice flows have been found to be growing faster than they are shrinking, despite fears over global warming. This is not the first time the Daily Telegraph has been moved to question data on global warming. Anyway, NASA scientists, they said, have shattered the conventional wisdom that Antarctica's ice surface is shrinking and reveal that the amount of ice is in fact growing. This was a new study published in the Journal of Glaciology, impact factor 3. All scientists bemoan the fact that the merit of their work is measured by the impact factor where it's published. And I will be the last to say that it's a reliable guide, but nonetheless we have two conflicting studies, and I hope that we're going to have some light shed on which of them we should put most credibility in. So here tonight we are very pleased, absolutely delighted in fact, to have two alumni of Churchill College, two graduates in natural sciences. Although I think he was going to speak second, I credited David with maybe having the idea for this, so I'll introduce him first. David Vaughan was a Churchill undergraduate in natural sciences, and it says 81, and I'm never sure, is that when you arrived or when you left, when you started, right? But he's currently Director of Sciences at the British Antarctic Survey, which is a Natural Environment Research Council institute based in Cambridge. He has responsibility for the strategy, funding, and delivery of BAS's entire research portfolio. He first went to Antarctica in 1985 as a surveyor's assistant and has since led 8 scientific field campaigns. He's published widely on ice, climate change, and sea level rise. He was coordinator for Ice2Sea, a major European-funded program to develop projections of future sea level rise, was coordinating lead author for the last 2 assessments of the Intergovernmental Panel on Climate Change, and as if he didn't have enough to do, is an honorary professor at Swansea University. Professor Eric Wolff, who's going to talk to us first, was a Churchill undergraduate arriving in 1975. He's currently the Royal Society Research Professor in the Department of Earth Sciences at Cambridge University. After graduating as a chemist, he studied ice cores from the Antarctic and Greenland for the past 30 years, using them to understand changing climate as well as changing levels of pollution in remote areas. He also carries out research into the chemistry of the lower parts of the Antarctic atmosphere. Until June 2013, he'd worked at the British Antarctic Survey, leading their program, Chemistry and Past Climate. He's chaired the Science Committee of the European Project for Ice Coring in Antarctica, which produced 800,000-year records of climate from the Dome Sea Antarctica ice core. He co-chairs the international initiative to coordinate future ice core research. His main research goal is to understand the causes of climate evolution over recent glacial cycles. And Eric was elected as a Fellow of the Royal Society in 2010. So I'm sure you can agree with me that we could not possibly have 2 people better qualified to talk to us, enlighten us on this important topic, and to resolve the issue of whether we should in future buy the Daily Mail or the Daily Telegraph. Eric.
Thank you. Okay, I have to hold this microphone, so try not to be too awkward. So, good evening. Thank you for coming. Now I feel really bad now that I've realised that I'm between everybody and their food and drink. So we'll try and make the time pass quickly by being interesting. So we're doing a double-hander here. David actually gets the difficult job of deciding whether the Daily Telegraph or the Daily Mail are right. Obviously, they're both wrong, so that's easy in a way. But he gets that difficult job because I'm going to talk mainly about the past and kind of set everything in context. I'm actually going to take a slightly, at least for the way I normally talk about this, a slightly unconventional route, which I hope will be interesting, of going right back in time to the beginning of Earth's history, and then get towards the present and set the scene for what David's going to say. So, going right back to the very beginning, what determines the climate of a planet? Well, it's actually, we're always saying that climate's really complicated and you need these huge climate models and there's thousands of equations and so on, and in a way it is if you want to know what the climate in Piccadilly is going to be in 6 years' time. It's really complicated. But if you just want to know the climate of a planet, it's actually not that complicated. There's really only about 3 things that can change. So there's energy arriving from the sun. Well, in our case, from the sun. If it's another planet, maybe someone else's sun. And then some of it's reflected away from light surfaces, of which ice is an obvious one. And the rest of it's radiated back to space as heat, as long-wave energy. And those are really the only 3 things that one has to play with to understand the climate of a planet. So essentially it means that at a planetary scale, climate is determined by the sun, its strength and the distance we are from it, by the colour of the planet, and that's where the ice really comes in, and by the composition of the atmosphere, essentially the greenhouse effect. So if those things get out of balance, then Earth will accumulate or lose energy, which means it'll warm or cool. So I'm now going to do that again, but this time with an equation. But it's the only equation, and it only appears for about 20 seconds. So here's the equation. So there are some physicists in the audience, so it's okay to put it up, but it won't be there for too long. You probably recognize the equation. There's a bit of Stefan Boltzmann on the right-hand side and some incoming energy on the left-hand side. And the only things that we can change in this equation, which is pretty good for a planet, actually, it's a pretty good exact relationship for a planet. We can only change those things. So if you know what they are, it's fine. If you don't, I'm about to tell you, but the equation's going to disappear. Okay, so if you change any of those 3 things, then the 4th one has to change, and the 4th one is the temperature of the planet. So the energy arriving at the top of the atmosphere, so that's the strength of the sun, which of course has 11-year cycles, but something else as well, which I'll talk about in a minute, and the distance, which is Earth's orbit. So when we talk about ice ages coming and going because of Earth's orbital cycles, that's what we're talking about. Then there's the albedo, so that's the proportion of sun's energy that's reflected, and that's to do with partly with what's on the land, whether it's ice or ocean or forest, and partly to do with what's in the atmosphere, so clouds obviously are quite white. And then the emissivity is basically how good a black body the planet is, so the proportion of heat that could be emitted that actually does, and that's really determined by the composition of the atmosphere. So normally in these talks we find ourselves going on and on about the 3rd of these, the greenhouse effect, but this is supposed to be a session about ice, so we'll go on and on about ice instead. Just to say, the albedo, that thing about how much of the energy is reflected, this is a map of albedo of the land surface, so the ocean is just blue because it's blue. There's no albedo of the ocean reflected there. The albedo of the ocean actually is only about 0.1 or 0.15, so not much is reflected. But you can see just by looking at that map that the things that give the Earth a high reflectivity are forests turning into deserts and anything turning to ice. So ice is really important for this and is actually the main determinant on long time scales. Okay, so now some examples. Okay. So the first one, this is supposed to be about ice, but the first one is a case of where's the ice gone? No ice, but why not? And this goes right back to the very early days of the planet. It's what's called the faint young sun. It's not my speciality, I should say, but nonetheless I lecture on it, so why not? So all stars, so I'm told by astronomers, all stars that are like the sun anyway, have an increased luminosity with age. So by looking at other stars that are like our sun, you can estimate what should have happened to our sun. And essentially, if it has a luminosity of 1 now, it should have had a luminosity of about 0.75 3 or 4 billion years ago. So with that weaker luminosity, that's a lot less energy getting to Earth. And that means, and that's what the band is, that either without an atmosphere or with an atmosphere, it should have been frozen. It should have been way below 0. And yet, there's lots of evidence that it wasn't. This is just one piece of evidence that I'm not qualified actually to explain to you, but maybe someone else in the audience is, which is pillow basalts in Greenland. They'd been dated to nearly 4 billion years ago, and they're an indication of liquid water. They're the kind of rock that only forms underwater. And there's lots of other evidence of water, and with a few exceptions, at this time, 3 billion years ago, no evidence of ice. And I'll show you in a minute what evidence of ice would look like. So we know what the solar energy was. It was less. So the only things we've now got to play with are the albedo and the greenhouse effect. And one can go through various things to do with that. One could play with the amount of clouds. One could play with the amount of continents, because ocean is darker than continents. But actually, even if you turned the whole world into ocean and had no clouds, it still wouldn't be enough to get you out of this problem. So actually, you're left, in this case, you're left with the greenhouse effect by a process of elimination being the reason why the Earth wasn't frozen at that time. And there are all sorts of molecules that have been looked at and then discarded. And there's been a suggestion there could have been more clouds acting as a greenhouse effect in the high atmosphere. Again, it seems you could cover the whole Earth with cirrus and it still wouldn't do the trick. So people think it's probably carbon dioxide, but you'll see I haven't left it black. The reason I haven't left it black as the definite answer is because, and I'm sorry about this very messy graph coming up, when you actually try and estimate what carbon dioxide was 2.5 or 3 billion years ago, it still isn't enough to stop the Earth from being frozen. Now, there are papers coming out all the time, and there was one last year that said, well, maybe it is. But nonetheless, this is a problem that isn't solved. Anyway, the ice part of this was just to say this is a time when there should have been ice and there wasn't. So now we're going to jump through about 80% of Earth history to about 700 million years ago, to Snowball Earth, so another iconic time in Earth's history. I'm sure you thought I was going to talk about the last few thousand years, which is why I decided to surprise you by talking about millions of years. So Snowball Earth, there were two major periods of Snowball Earth around 700 and 600 million years ago. And what do we mean by Snowball Earth? We mean there was ice covering the Earth at very low latitudes, meaning that pretty much the whole Earth was covered in ice. There are actually different proponents of Snowball Earth have different ideas about what it would have been like, whether it would have been fully frozen or whether there had been a small area of still open oceans near the equator. So how do we know that? Well, people have found evidence of ice at low latitudes. So they know it's low latitudes by looking at the paleomagnetism. So that's the magnetic field in the rocks is horizontal compared to the bedding, horizontal rather than vertical. That implies that you're at the equator. And we know it's ice because you see things like these. Oops, I knew I was going to do that. That's a drop stone. You can only get those into sediments out of an iceberg. And that's scratching that can only come from ice going over a surface. And in both cases, these are at low latitude. So we had a very cold planet. So why did we have a very cold planet? Well, I know I'm going to state the obvious chicken and egg thing. Very cold planet because it had a high albedo. There was lots of ice. So that's not a very interesting question. There was lots of ice and it was cold. But the question is, how did it get into that state and how did it get out of it again? And to discuss that, I need to show a hysteresis curve. But again, if you're not a physicist, you don't need to worry about it. I'm going to walk you through it. Essentially, all this is saying that we can calculate what CO2 concentration you would need, so what greenhouse gas effect in the atmosphere you would need in order to get a particular temperature if the Earth was more or less ice-free. And you can do the same calculation if the Earth was more or less completely covered in ice, and that's these lines here. And the way you have to get into a greenhouse is that you come along here and get colder and colder by reducing the CO2, and eventually you hit the end, and the only place to go is to a fully glaciated Earth with completely covered in ice. The problem with that is that once you've got into it, once you've got into it, you can only get out of it by going all the way up to incredibly high concentrations of CO2 or some other greenhouse gas, so that you can jump back onto the ice-free pattern, because the cold planet wants to stay cold because it's covered in ice and it's reflecting all this light away. It's no longer got anything to keep it warm. So what we think happened, but again it's not proven, but there is good evidence that CO2 was involved. What we think happened is the result of what controls the CO2 concentration on million-year timescales. This has almost, what I'm about to talk about, has almost no influence on the scale of 10,000 or even 100,000 years, but over very long time periods it does. What you have is the weathering of silicate rocks removes CO2 from the atmosphere, but eventually from the ocean as well, and volcanism re-emits it to the atmosphere, and hopefully at the same rate. It's a very small rate, it's about 1% of anthropogenic emissions, but it's enough over millions of years to make a difference. And so what we think happened is that what initiated the snowball was increased weathering, and the reason for that was probably, it's what's in the literature, it's not that probable, but it was what's in the literature, was probably the fact that the continents were clustered at the tropics, and the tropics are a really good place to get weathering because you get warm temperatures, which is good for weathering, and a lot of rainfall, which is good for weathering. So that drew down the CO2 concentration and put it into the snowball. And now we've got this snowball, the whole Earth covered in ice. There's no longer any weathering. There's no longer any rocks to weather. There's no longer any exposed rocks for any rain to get to. So the volcanism's still putting out CO2 at this very slow rate, but nothing's taking it out again. So you can get to very high concentrations, and there's evidence that we did, and that gets you out again. Okay, now let's jump through another 80% of the remaining time of Earth's history. And we're now looking at 50 million years to the present. And what you're looking at is, well, you're looking at the oxygen-isotope ratio of shells in marine sediments. But what this is telling you, it's effectively telling you the temperature, at least in this part of the diagram, and then it's telling you how much ice there was on Earth. I could explain in a question if anyone wants why that is, but just accept it for now, please. So what you see over 50 million years is the Earth slowly cooling and then starting to get ice, and that's actually the East Antarctic ice sheet starting to form, increasing amounts of ice, and then eventually this part is where it gets interesting to me. So this is supposed to be the history of ice on Earth, so that's the history of the last 50 million years. Now we're just going to do the last 4 million, 5 million. So you're seeing exactly the same plot here, actually, it's just it's stretched out now. So what you're seeing here is not very much happening. There's already an Antarctic ice sheet here, but not very much happening. But here you get these oscillations. And what these oscillations are is ice sheets coming and going in the northern hemisphere over North America and Europe, with increasing amplitude as time goes on, and with a varying time period between them. So these are the ice ages. These are the ice ages. These are the warm periods, the interglacial. This is where we are now. That represents a sea level range of roughly 120 meters. So that's what you can draw down by putting ice in the northern hemisphere over North America and Europe. And to give that scale, if we were to get rid of all of Antarctica, we would go up another 60 meters above that, as I'm sure David will discuss. So finally we get on to what I do, which is look at the last few ice ages by drilling ice cores in Antarctica. I think I've got time to show the video that comes next, assuming it works. So the ice cores, just to say the ice cores, that's what they look like. They're about 10 centimeter diameter. They come up a couple of meters at a time. And they have these bubbles in, and that's the thing they're most famous for, these air bubbles. When the snow compresses to solid ice, you get these air bubbles that you can crack open, and they contain a sample of the atmosphere. So here's a video of drilling an ice core for a bit of light relief. I don't mean drill the ice core for light relief. I mean, I'm showing it to you for light relief. So that's the tent where you drill in. It looks as though he's drilling into wood, but actually that's just wood to stop snow going into the hole. So the drill's going down into the hole that's already been drilled. It's on a wire. They're at about 2,400 meters at the moment. If anyone's heard my talks before, they'll know I always make this joke at this point, that there's some rule that the drillers sit in a heated cabinet while the scientists freeze to death outside, so that's what I was doing. So now 2 hours have passed and the drills come to the surface again. And you can see the ice glistening in the end there. You can see the cutters. It's a fairly simple tool at heart. He's trying to look intelligent because he knows he's on film. And they're about to do the most important thing you can do to a core, which is to put a pencil mark with an arrow on it pointing upwards, because it's really unfortunate if you turn 1,000 years upside down. You can write on ice, by the way, so try it in your gin and tonic sometime. And there are the drills. It's actually already been cut at that point to give a straight edge. And it's just resting for a bit before we do anything too serious to it. And it's minus 25, as you can see. And in the field, this was one of my last couple of field seasons where I was field leader here. We basically were doing woodwork. We were cutting the ice up into different sections that would go to different labs in Europe. Some of the analysis done in the field, but mostly done in Europe. And cut into all those sections that you can see there. And then packed into boxes to go back to Europe, insulated boxes. That one's not insulated anyway, but eventually it'll be in an insulated box. And I'll just stop him and move it on. Okay, so that's how you drill an ice core in 2 minutes. And this is the kind of information you get from these ice cores. So this is actually, it's oxygen isotopes in the ice. So it's the oxygen isotopes in the ice tell you about the temperature at the time. Actually, it's deuterium in the ice, I apologize. Deuterium to hydrogen ratio in the ice. This tells you about the temperature at the site where you're drilling. And what you can actually see here is 800,000 years to the present. And we've got the Holocene, so that's the last 10,000 years of relative warmth. Then we've got the last glacial, so that's the period when there's ice ages over Northern Europe and North America, but it was also about 10 degrees colder in Antarctica. Then the last interglacial that I'll come back to in a minute, a little bit warmer than the present in Antarctica. And the previous glacial, and so on, 8 glacial cycles. There's roughly 8 glacial cycles of 100,000 years here. And this is the longest ice core record there is. I'm just involved in trying to spin up a project to get older than this, back to beyond 1 million years. It's certainly going to see me past my retirement date before we've got the ice. So do support it and listen out for it, but don't expect it immediately. So as well as getting the temperature, we can get the CO2. That's from these little bubbles where you can crack them open and measure the concentration of nitrogen, oxygen, argon, CO2, methane, whatever you want. And you can see they look very similar. The CO2 and the temperature are moving in step. Again, we're into chickens and eggs, so the temperature is somehow causing the CO2 to come out of the ocean, and the CO2 is helping to amplify the temperature increase. I'm just going to concentrate on this very last change from the last ice age, 20,000 years ago roughly, to the towards the present. So just to give you a feeling, because I keep talking about ice sheets, that's an artist's impression of what the ice sheets look like on the left. So on the right is present day. I know Antarctica looks a little bit strange. That's why I say it's an artist's impression. Noah obviously couldn't afford a proper artist. But this is what it looked like. The Antarctic ice sheet was a little bit bigger. There was more sea ice. But over the north, you've got ice down to, well, in this case, of the last glaciation, Wisconsin. That's why it's called the Wisconsin in North America. And over Europe, it goes down. It covers Britain and Scandinavia and a lot of Northern Europe. So that was where the 120 meters of ice went. 120 meters of sea level went, rather. So this is those same plots of CO2 and temperature, the temperature in black in each case and the CO2 in the dots, with 2 different methods and 2 different cores coming out of the last ice age from 20,000 years ago to 10,000 years ago. You can see they're moving nicely in step. What you've got, coming out of there was a net global warming of about 5 degrees. So that's, when you average over the globe, that's a good number to remember, because sometimes we talk about the future having a global warming of 2 degrees or 4 degrees, and people think that's not very much. Well, 5 degrees was the ice age to the present, so maybe that gives you a scale for how much 2 or 4 degrees is. It was triggered by changes in where the sun's energy is arriving, so that's changes in the Earth's orbit. It meant essentially the northern hemisphere in summer was facing the sun when the sun was closest to the Earth in its elliptical orbit, which means that it gets more heat in the summer in the northern hemisphere. That helps to melt ice sheets. So that's what triggered it. But it's not exactly what caused it, because if you looked at the energy balance 20,000 years ago and today, they're almost identical as far as the Earth's orbit's concerned, because you've gone through one complete cycle of the orbit. So if you actually said, why is it different now from 20,000 years ago, the answer isn't the orbit. That's the answer to why it happened, but it's not the answer to why it's different. The answer to why it's different has to be due to changes in albedo and greenhouse gases. The albedo because the ice sheets went and the sea ice reduced. The greenhouse gases because the CO2 went up. And our best estimate is it's about half and half, those two things. So the narrative is that the changes in Earth's orbit led to some ice melt, which led to a change in ocean circulation, which led to the CO2 being released from the atmosphere, which amplified everything else. The ice melting caused a change in albedo, which also amplified everything else. Okay, so finally, before I finish, I'm not really quite aware of the time, but I think I'm just about all right. I want to talk about the last interglacial as a setting for what David's going to be talking about. So I've been talking mainly about times when there was more ice. Now we're going to talk about a time when there was less ice, which is more relevant for the future. So the last interglacial is here. This is Antarctic temperature. You can see that it's jumping up above the present. So Antarctica was warmer, at least at some point in that last interglacial, which is 130 to 115,000 years ago. So now I've put an Antarctic temperature and a Greenland temperature on top of each other. The blue line in each case is today's temperature. There. So Antarctica, you can see, was warm in the early part of this interglacial, and Greenland was also warm, but actually in the later part of the interglacial, not at the same time. We don't actually have a record from back here, but we're pretty sure it carried on and was cold at that early part. Don't take too much notice of this number here. That's too high, in my opinion. There's other papers come out saying that that should really be about 4 degrees rather than 8 degrees. But still, both polar regions were warmer. The tropics were probably a little bit warmer as well, but that's not part of this story because we're worrying about ice sheets here. So they were warmer, but not simultaneously. And we've got estimates of sea level in the last interglacial. Now, getting sea level in the last interglacial is a tricky business. The way that it's, or at least the way that many of the estimates on this plot, which I'll talk about in a second, were made, was from corals. The idea is that you look for corals on land that are therefore clearly above sea level, but obviously when they were formed, they must have been below sea level because corals form below sea level. But you have to then correct for various causes of uplift of the rocks, one of which is tectonic, but you go to places that are tectonically inactive. But the other one is isostatic rebound from the removal of ice sheets. So you need to go somewhere that's a long way away from ice sheets, from where ice sheets used to be, in order to remove that effect. Anyway, the people who do this, who were represented in this paper, they believe they're very expert at doing that. And so their estimates of, they can measure the age of these deposits, they can see how high above sea level are, they can make the correction. And what they've plotted on here is the last 14 estimates, going back over a decade, of sea level in the last interglacial. And you can see that they cluster somewhere around 6 to 9 meters higher than the present. Now, I wouldn't absolutely stake my own life on this, but nonetheless, that's what the evidence says. There's no evidence to say anything other than that. So 6 to 9 meters is quite a lot. And the only places we could get it from are the Antarctic and the Greenland ice sheet. You can get about a meter by melting all the other glaciers on Earth and by raising the volume of the ocean, because as it gets warmer, the volume of the ocean increases. You can get a meter, maybe a meter and a half out of that. But everything else needs to come from the ice sheets. So the conclusion of this review paper, in a journal with an impact factor of 30, which proves nothing, was that actually Greenland probably didn't contribute that much, but Greenland could, in theory, contribute 6 or 7 metres, but the conclusion was that it was probably only 2 to 4 metres. That's partly because we have found last interglacial ice in various places in Greenland, so clearly the whole ice sheet didn't go. But it doesn't matter for this story. What matters is that something, I mean, if it isn't Greenland, it has to be Antarctica, but whatever way, something caused 6 to 9 metres sea level rise under a climate admittedly sustained for thousands of years, but a climate that was not very different from what we're expecting in 2100. So that's one of the things that concerns and motivates me to worry about sea level. Now, obviously, sea level takes a long time to rise. It takes a long time to get rid of an ice sheet, and this had thousands of years to do it, and we won't be around to see it. But nonetheless, at some level, we probably ought to be worried about it. So in summary from me, the presence or absence of ice has been a key characteristic of Earth's climate throughout its history. It's probably the most obvious thing you would see as an extraterrestrial looking at the Earth that was changing about the Earth. It's the major player in global sea level change. The past highlights the way that ice, greenhouse gases and climate have been intimately linked over all geological timescales. And then the last interglacial poses a worrying question about sea level in the face of sustained warmth. I don't think we can say exactly why sea level rose as much as it did, but David will be addressing that to some extent. And that obviously leads on to the question of what's happening to ice sheets today. And with that, I will pass on to my esteemed colleague.
Okay, thank you very much. I will leave. Need the microphone. I will leave the question about the Daily Mail or the Daily Telegraph to the end, but I will tell you I have published quite a few papers in Journal Glaciology, that shoddy, low impact factor journal. But we'll come to that at the end. So I'm going to talk a little bit about sea level rise as we're seeing it at the moment and as we'll see it in the future. But just before that, Eric's employer did not need any introduction, University of Cambridge, to anybody here. I will just say a little bit about BAS. British Antarctic Survey is one of 6 research centres that's owned by the Natural Environment Research Council. And the others that you can see there, we are tasked with doing strategic science and delivering a programme of strategic science that addresses issues that are of significance, not only in the Antarctic but also in the polar regions in general, and we're even going further afield now into other areas. We also provide logistics support to the much larger UK community of scientists who want to work in Antarctica, and every year about this time we will be taking new batch of new and old scientists to Antarctica to do work who come from UK universities, overseas collaborators, and of course our own. This is me in the 1980s. This actually is, although this is a picture of when I first went to Antarctica, it is actually to indicate that Churchill, well, this Churchill graduate didn't fall very far from the tree. The British Antarctic Survey is actually based, well, possibly a kilometre away from Churchill. If you drive out of Cambridge on the Madingley Road, just before you hit the M11, you go past a rather spectacular tent-like building, which is not us. We're the little squat building next door, but just before the M11. That's British Antarctic Survey. We run in the Antarctic 5 stations, 2 that are running through the winter. We run 2 ships at the moment and 5 aircraft, and those are provided to the UK community in their entirety for scientists. I actually have a team of about 130 scientists working across a range of scientific topics, from providing advice to the Southern Ocean fisheries on what catches should be allowed, to looking at space weather. Antarctica is an excellent place to look at the flux of particles in from the sun that damages satellites and limits their lifespan. And then to my own interest, which is glaciology, ice, and its effect on sea level. I'm going to give you just a very little background on sea level change, contemporary sea level change, and then we're going to move into looking at what might happen in the future. Sea level is, exactly as Eric has pointed out, the conglomeration of a whole bunch of factors, some of which are global and some of which are local. Ice sheet melting is the biggest, or ice sheet change. The change in the amount of ice that's stored on land is the biggest effect, if you look in those geological terms. But then this thermal expansion of the oceans, as it takes up heat from the atmosphere, is a fairly rapid change that can occur over the course of decades to centuries. Changes in salinity, meaning areas where the ocean starts to evaporate more rapidly and the surface layers will get more saline, can have an effect in a local sense, as can ocean circulation, the ocean piling up on eastern coasts due to changes in ocean circulation, and the vertical land movement, again Eric mentioned, that can be a response to the removal of an ice sheet and then the consequential 10,000 years of slow uplift, or a little further away, the other side of that seesaw effect, where the land actually subsides for an equal period of time. And then the one that many people forget about is this direct anthropogenic change in sea level, which is the production of reservoirs, which is essentially taking water that will, coming out of the oceans, storing it on land, forces sea level down. In a cumulative sense, that is actually not a dominant signal, but is certainly one that we need to take account of. And the contrary signal, which is extracting groundwater, using it for irrigation in one agricultural cycle, and then it ends up in the oceans, adding to the oceans. If that's not replenished, then we have an additional sea level rise. Sea level around the planet is rising and has been rising now for the period over which we can measure it. This diagram comes from 150 years of tide gauge data, measured around the coasts, much of it in Europe, but further afield as well. And then in the last little period, you can see a dense black line there from satellites. We've seen overall an increase in the rate of sea level rise from the late 1800s up to the present day. One of the important things to see about this diagram is sea level, as opposed to climate change or temperature, is pretty much a one-way street. Once you've taken water out of the glaciers and ice sheets and put it in the ocean, it's going to take a long time to get it back into the glaciers and ice sheets. If you get heat into the ocean, causing thermal expansion, then again, it's going to be a long time before that reverses. So we tend to think of sea level change as being pretty much one directional on a decadal sort of timescale. This is the map of recent sea level change, so not over 100 years, but actually over that 2 decades, measured from satellites, and it's very, as you can see, very patchy across the Earth. Certainly if you are in the equatorial regions around here, you might have been seeing some sea level fall and sea level rise in this area. Those of you that know your meteorology will know that that pattern is actually rather similar to the El Nino Southern Oscillation pattern, and yes, it is quite related through these dynamic dynamic effects on the ocean. So sea level is not a uniform thing, and the shorthand that I use global sea level rise is exactly the same shorthand that we would use to talk about global warming. In a sense, nobody sees global warming. You see the regional warming that happens on your own doorstep. You don't see global sea level rise, you see some version of it that might be up and it might be down. But overall, we can put a number on it. This is my wife, actually. She describes this as, does my beach look big in this? The impacts of sea level rise, that's the same beach, are actually worth thinking about because they actually condition the question that we as scientists have to answer. This is a beach in the Outer Isles of Scotland. Harris faces out into the Atlantic. It's a beautiful place. Just to take a role for the Outer Isles Tourist Trust, you've really got to go here. It's beautiful. On a lovely summer's day, it beats just about anywhere else I've been. And it has this very unique ecological environment, the Macaire, which lives in sympathy with the sea. It lives inland of a beach that is made up of seashell fragments, and it can tolerate quite high salt conditions. Can't tolerate often flooding very often, but it can tolerate the proximity to the sea, and we'll come back to why that's important in a little while. What else do we have in the coastal zone? Well, we have things like Sitewell B down on the Suffolk coast. Sitewell B, well, I actually use it because this is a site where we as a nation are now currently discussing whether to build Sitewell C. If we build Sitewell C now, it will probably take another 30 years. Well, I suspect it's going to take 10 years for anybody to agree to it. Then, let's say another 30 years to build, run it for 50 years. Certainly then we're going to need to have another 50 years to decommission it. That gives us a good timescale on what our projections, how far our projections of sea level change should reach into the future. A nuclear power station that's built within sight of the sea because it wants the water to do its cooling with. Fukushima has shown us that we actually should be very careful about how we site and how we plan the protection for such an installation. And we need to think of it over 150 years. We have many coastal cities around the world, such as this is Rotterdam, which have these fantastic protection systems. These are gates that close across the river to provide a level of protection. Obviously, Rotterdam is a port. We need to be able to access it, so you can't close the river off completely. You need to have this system that can be shut down when there's forecast of high storms. Understanding this risk actually understands, again, preconditions tells us as scientists what sort of level of precision we should be getting to. So I'm going to give you a few reasons why I don't think the level of confidence that we have in projections at the moment is sufficient to answer the questions. These are some areas around the UK coastline and in Northern Europe that are actually vulnerable because they are rather close to sea level, already within a metre. But long before we get a metre of sea level rise, these areas will actually become untenable because they're being flooded too frequently by storms to be usable. Here's London, and this again is a city on a tidal estuary, and it has a twin flood problem. It has, if you look down here, the Thames barrier here, we have tides going up and down here, and this is off to the open sea, North Sea, and occasionally during the winter, usually during the equinoctial storms, around now or end of January, we have big storm surges that come up down through the North Sea. As they come into the shallower water, the storm waves get bigger. Actually, the long period waves get bigger and send these occasional big storm surges up. So we need to protect from the sea. We also need to protect from river flooding. Rainfall flooding comes mostly in the summer with big thunderstorm events and is exacerbated by the amount of concrete we have in Greater London, which causes runoff very, very rapidly into the River Thames. And again, we need to be able to get rid of that water as well as being able to protect ourselves from water coming the other way. Actually, the Thames Barrier is used for both of those things. It can allow us to, we close the Thames Barrier if there's a flood and then let it out to really get the stream of the Thames going more rapidly at low tide. So in the past we've been very responsive in the way that we've protected London and other cities around the world. Essentially these are the Thames sea defences just at Trinity Hospitals on the south side of the river, just upstream of Greenwich. You can see Trinity Hospital just poking out there. And you can see that we've actually raised our sea defences several times in the past century and a half. And in each case that's been in response to a big flood event or near flood event. The last of those was 1953. There was a big flood, storm surge that came down the North Sea and killed about 200 people, just less than 200 people in the UK, and rather more in the Netherlands, probably 1,800 in the Netherlands. And we, in the face of that, built another 6 inches on top of the sea defences to keep us safe. That was going to work. Actually, we did rather more than that. We started thinking about our larger sea defences, the Thames Barrier, after that event. It took us 30 years to build it. It will take us another 30 years to replace the Thames Barrier, and depending on how we decide to replace it, whether it's a new and bigger barrier, whether it's a re-engineering of the existing system, it will take several decades to replace. Thames Barrier was built considering these statistics of storm surges and their likely recurrence rates. So if we look at this, it's based on the storm surge that we expect to get every year. And the height of that is given 0 meters, and everything above that is comes less frequently. So every 10 years we get a storm surge that's about 0.4 meters higher than the one we get every year. Every 100 years, every 100 years we get a storm surge that is another 40 centimetres above that 10-year one. So, it's 0.8 metres higher than the one we get every year. In 1,000 years, it's something about 1.4. Very non-linear in the sense of the return period. The Thames Barrier was built to give us this level of protection at about 1 in 1,000 years. But, of course, if we raise sea level, in this case by a metre, we would then drop that level of protection to 1 in 10 years. Now, 1 in 1,000 years is probably acceptable to most people living in London. 1/10 of a chance that it's going to happen in your lifetime. Once in 10 years, very much not acceptable. So somewhere between these two, the Environment Agency needs to work out what is acceptable and how to manage the risk so that it stays at that acceptable level. Go back to this Macaire environment. The Macaire can cope with sea level rise, but only at a certain rate. If the rate exceeds it, essentially it will become too flooded and the environment will be damaged. Here, the statistics are quite different. They're very much flatter, which reflects the fact that they are out into the Atlantic coast and they not at the head of the North Sea, where the storm surges are piling up in the same way. So here you don't get the big occasional 100-year storm event that's that much higher than the one you get every year. It's much more of a flat perspective. And here, it's actually much more sensitive, because a change in sea level of only 20 centimetres actually will change the risk of a 1 in 100-year storm. Well, we'll put it down to about 1 in 11, 1 in 12 years. So this is a very sensitive system. So those things actually condition the types of projection that I, as a glaciologist, believe we should be offering, and the confidence levels that I would like to produce. I need to think about the Earth at least 150 years into the future, and I need to be able to give you a level of sea level rise that's essentially down at let's say, 10 to 20 centimetres of confidence. There are, in the world, many glaciers. They exist on every continent, and this last glacier inventory, which essentially counted them all, like holes in Blackburn, Lancashire, they're very small, some of them. But I say that there are 198,002 glaciers. The 2 glaciers that weren't counted in this are the ice sheets of Antarctica and Greenland. These glaciers, because there are so many of them, because they are very well distributed across the Earth, are actually in some sense quite predictable. And Eric said, if we took all of these glaciers and we melted them all, we would get about 0.5 metre of sea level rise globally. Locally, you take what you get, but globally, you've got 0.5 metre of sea level rise. That's not going to happen because in the Himalayas at more than 20,000 feet above sea level, whatever we throw at climate change, there's still going to be ice up there. So we might look at how much ice we could get out of the ice sheet, the glaciers, mountain glaciers, and be looking at about 25 to 30 centimetres over the next 100 years. The big ones are Antarctica and Greenland. Antarctica has enough ice in it to raise sea level by 60 metres globally. It isn't going to happen again because, as Eric pointed out, the ice has been locked in Antarctica for around 30 million years, and it would take an enormous change in climate compared to present to extract that ice. However, there are areas of the Antarctic ice sheet which are more vulnerable, and those are the areas we're actually looking at. Greenland is in a warmer environment and is probably more vulnerable to, well, certainly to some atmospheric warming. So there are these big sources of ice and sea level rise that we actually find much harder to deal with than all those glaciers that we can just put into a statistical model. The reason is that there are only 2 of these glaciers. There are only 2 ice sheets, and if we get either wrong by even a relatively small percentage, we could get the whole number wrong quite badly. So those big numbers, about 60 metres of sea level rise, are really illusions, and this is a much better way of looking at how much potential there is for sea level rise from the glaciers and ice sheets. Glaciers and ice sheets have snowfall into them every year that is equivalent to about 2 millimetres of global sea level. So a layer of global sea level of 2 millimetres across the whole ocean, take it off, and it falls as snow onto the glaciers and ice sheets. Most of that then comes out in the same way. Most of that then comes out, running off the glaciers into the rivers and streams, and then eventually into the ocean. So this is the flux per year through that glacial system. Greenland, as a single ice sheet, almost matches that. And Antarctica, well, outbids it considerably. 6 millimetres of sea level goes into the ice sheet, around 6 comes out. So any imbalance in any of these numbers between the input and the output actually means, essentially drives the sea level change. I've also shown in this graph what comes out as meltwater that's already been melted in situ on the glaciers or on Greenland, or a very small amount in very cold Antarctica, and what comes out as icebergs or melting directly into the ocean, and this doesn't go through that melt and streams. And that also tells you a little bit about where the sensitivities are for this. Glaciers are going to be affected by atmospheric temperature change. Greenland's probably going to be affected in the same way by the ocean change and the atmosphere change. And Antarctica, it really only feels the oceans. This is what's happening in Antarctica. This is data from a satellite which was flying from 2003 to 2007, and these are elevation changes that we measure directly from that satellite. Here are areas all the way through West Antarctica that are losing ice up to, well, around 1.5 meters of ice per year. There is an area over here which actually looks quite strongly as if it's getting thicker, and it is getting thicker. The reason is that this glacier essentially switched off around 140 years ago, stopped flowing, and so the snowfall that should be being removed by that glacial flow is actually just piling up, and it will continue to pile up until it's eventually thick enough to drive the glacier forward again. So there's patchiness here. There's even areas where a couple of years of high snowfall in this period showed thickening in the ice sheets. But this is the area that we're really concerned with. A few areas over here. In Greenland, there are similarly very specific glaciers that are losing ice. We can measure that in a completely different way. I'm just going to look at my watch. And that way is using this satellite pair called GRACE. This is one of the coolest things that I've been involved with since I'm involved with it only in the sense that I've used the data. I was not clever enough to think that this was a way of actually measuring anything on Earth. It's very, very clever. It has two satellites that do almost nothing except measure the distance between them. And that distance is controlled by the gravitational forces on the Earth and the changes in the gravitational forces. So as the first satellite flies over, let's say, a mountain chain where gravity's a little bit high because there's a lot of rock there, it will actually accelerate as it falls towards the mountain, and it gets a little bit further away from the satellite that's following. And then on the other side, the other satellite catches up with it, and just by measuring the distance between those two satellites, you can measure that mountain chain. You can actually measure the weight of the ice sheet. So you're not measuring the elevation, we're actually measuring the weight directly. And for Greenland, where there is a strong winter snow accumulation and summer melting, you can actually see that cycle. In Antarctica, there is no summer melting, and the snowfall just arrives when it arrives. So you can actually not see that seasonal cycle. But for both of them, you can see that there is an acceleration in the rate at which they are losing ice into the oceans. And Greenland, is stronger at the moment, but Antarctica is accelerating as well. A little bit of an aside. So where are we with projections of sea level rise? I was involved with the last Intergovernmental Panel on Climate Change and its projections. I actually wasn't involved in the sea level chapter. I was involved in the cryosphere chapter. But this process produced a set of projections, actually produced one very nice piece of science. It essentially, it was published in papers before it went into this, but it was almost commissioned as a challenge to scientists, the scientific community, to see if they could do this. This is the closure of the sea level budget. We couldn't do this before 2013, but now we can measure each of the contributions to global sea level rise, thermal expansion, glaciers, Greenland ice sheet, Antarctic ice sheet, land water storage. We can sum those up, and thank goodness they actually overlap quite well with the observed sea level rise. Previously to this assessment, we actually couldn't do that, and we could do thermal expansion, glaciers, and the Greenland ice sheet, but we actually used to just lump everything else and say that must be Antarctica. So this is a real proof now that I think that we can really with some confidence understand where sea level rise is currently coming from. The IPCC produced projections of many things, and the key ones that I'm going to show you are temperature and global sea level rise. This is the global temperature projections, and it's looking out, it shows you what's happened in the past for context, and then looks out into the future to 2100. I would argue 2100 for sea level is not far enough, but that's as far as the IPCC went. And let's go back. So the projection for temperature rise, and Eric kind of mentioned this, is for high carbon emission scenarios. We're looking at something that centers on around 4 degrees centigrade by 2100. You can think of that in terms of that number that Eric was using for the transition from glacial to interglacial. For a low and very, very optimistic scenario of carbon emissions, we might stay to below 2 degrees C. But there are a couple of other scenarios in the middle here which tend to overlap. Now, the reason I show you that is not to focus on the numbers, but to actually show you that there is, at least for temperature, a quite separated path for what we expect from those two emission scenarios. For sea level, we are still not so sure. Essentially, for the high emission scenario, we have sea level rise expected to be something between, well, something over 50 centimetres to something over a metre. And the low emission scenario, well, overlaps that at the higher end. In part, that's because we still don't have any skill. Don't have enough skill in predicting the future of the ice sheets and the glaciers. In part, it also it results from the fact that we have climate change that's locked into the system already, and we expect some temperature rise for even a low emission scenario, even for no emissions, further to what we've already put into the atmosphere. So there is a sense in which sea level rise is going to happen no matter what we do from now on, but it could be worse or it could be better depending on the emission scenario. So this is my bleat as a glaciologist as to why we can't do better at the moment. It's a list of things. The first is that sea level is very much at the end of a cascade of uncertainty. Let me tell you what I mean by that. I mean, we are uncertain about future emissions of carbon dioxide and methane. That means we are uncertain about future global climate. In terms of regional climate, we know less. And the uncertainty is magnified. And how that affects the ice sheets and glaciers is magnifying that uncertainty even more. By the time we get down to really trying to think about regional sea level rise, actually there is an unavoidable increase in that level of uncertainty that we can't avoid at present. And only really when we start nailing down all of those factors in the cascade do we really get to be much more certain about sea level rise. Second thing is that there are potential for instabilities in ice sheets that we really don't know much about. One of those is that much of that part of Antarctica that I showed as having high rates of ice loss at the moment, the red bits, sit on rock that's way below sea level. And if we start to remove some of that ice and it floats out of contact with its bed, then it will rather rapidly move away and thin and produce icebergs and add to sea level rise. If that potential instability is actually forced by climate change, then it could be kicked off, and this is what some people refer to as tipping point. We've seen in the geological record evidence that this has probably happened, but certainly in nobody's lifetime, and certainly not in the recent geological past that Eric could reach into, can we have really very strong evidence that this has happened in the immediate past. We know that ice has come out of Greenland and Antarctica, and this kind of mechanism could certainly explain why it was rapid, but we haven't got strong evidence for the fact that this has happened in the past. When we do produce geological evidence that this has happened, and when it happened, it will be a major improvement in our understanding. And that geological evidence sits there. It's here. It's underneath the ice sheet. And when we can drill through the ice sheet, it's a mere couple of kilometres of ice, and reach in and get those samples and tell us when this last happened, we'll actually be a lot more confident about future sea level change. Sea level is actually about weather rather than climate, and this is a bit of a subtlety again for perhaps people who are involved in physics. A weather model is one that you start off and you get it travelling in the right direction at time zero, and then you use that to make a prediction in the future. A climate model really doesn't matter where it crosses time zero, so long as the statistics are about right. So you can run a climate model for 1,000 years, say it's spun up, The statistics look right for present day, and then you make your projection to the future. A weather model needs to be spun up to today's conditions if you want it to predict the future. Ice sheets are like the weather, but they react on century timescales. And so they need to be set up so they pass today, or at least this decade, going in the right direction. And until we had those maps of where changes were occurring, we really had no way of pushing our models in the right direction. I'm not going to go into modelling. We also have a poverty of data. Ice sheets, essentially, when they march out across the continental shelf during a glacial period, they wipe out a lot of the record of what's gone on before. So we're very reliant on just that last retreat over the last 10 to 20,000 years to give us data that we can test our models with. Again, it's there in the geology. These rocks have a chemical signature, an isotopic signature, that tells how long they've been exposed to cosmic rays. Essentially, how when the ice collapsed around them and left them exposed on the mountains in Antarctica. The mud around Antarctica has a record in it that we can use in a very similar fashion to track the retreat. Ice should be very simple to model. It's a very homogeneous material. Has no turbulence in it, no Coriolis force, none of those things that make the meteorology, the atmosphere, difficult. But it's all in the boundary conditions. The ice and the ocean, the ice and its bed. The ice bed changes, in this case, high-resolution image of the bed of Antarctica. It changes across this transition. This is all water-saturated sediment, and then across a space of 1 kilometre, it goes to actually rather dense sediment that drags on this piece of the ice. When we scale that up to looking at the entire Antarctic ice sheet, an area the size of the US, the contiguous states of the US, then we have a great deal of unknown boundary condition in our models. What else am I going to say? Well, let's skip over some of these. I am going to say that one of the things that's helping us is that Greenland is probably like Antarctica will be in the next 100 years. Greenland is an ice sheet that exists in that warmer climate, and if parts of Antarctica warm over the next 100 years, they may end up looking pretty much like Greenland. So why is it hard to predict the ice sheets? Because it is. We don't have the certainty at the moment that would allow me to answer those questions that I think the stakeholders want. And then the stakeholders actually throw a real googly at us, and they ask some quite difficult questions. I went to talk to some people in Corpus Christi, and one of the guys that I talked to was a sea defence planner for the state. And he said, actually, I need projections of sea level rise for the next 100 years, because if I start protecting an area, if I build sea walls and sandbanks and protection and then remove it later on, I will be sued. This is purely a function that he needs sea level projections because of the legislative system that allows the landowner to sue the state. Don't have that in the UK. In other areas in the States, of course, North Carolina, they've actually decided that they won't plan using any projections of sea level rise that are greater than the current rate of sea level rise. This is another approach to sea level, which is just, well, literally sticking your head in the sand and hoping the sand won't get flooded. In the UK, I actually think we're in a better place. The Environment Agency understands sea level rise. They understand it for the Thames. They understand it for the rest of our coastlines. Doesn't mean they don't ask me difficult questions. If I go and talk to the Environment Agency, who protect London, they say, we have almost an infinite budget to protect London because the taxpayer wants the capital to be protected. So all we're really interested in is making sure that we can protect London against the highest rates of sea level rise that we can envisage. Just tell us, they say to me, about the 1 in 20 chance, the 95% upper likelihood for sea level rise. And obviously we can try and put numbers on those. Very difficult for us to, because it includes a lot of exceptional responses. If I go down the corridor and talk to the people who are involved in protecting the East Coast, Norfolk, the Fens, Lincolnshire, they say, don't tell us about the 1 in 20 chance. We're never going to get a farmer to pay money to protect himself and his land against a 1 in 20 chance of sea level rise. You must give us the best guess, the 50-50 chance. But again, actually, as a scientist now, if I go and actually talk to these stakeholders and frame the question in a way that makes sense for them, then I think we can do a much better job, and we can, at least for sea level rise, help protect coastlines where we can and help predict the risk to the coastlines that we can't. And I'm going to end there. Thank you very much.
We have questions billed, and so I invite both David and Eric to sit down and not rest on their laurels, but to take anything you can throw at them. And don't be shy.
In Eric's single equation, was the actual heat produced by the Earth itself?
I should have said that, actually. No, is this one working? Yeah. I should have said that, actually. I normally remember to say that when I'm showing that. So there is a little bit of heat coming out of the Earth, but as soon as a planet forms a crust, the rate of heat coming out of the centre of the Earth is small enough to more or less ignore it. I mean, it's what, 50 milliwatts per square metre as opposed to 1300 watts per square metre, so from the sun. So
You can't ignore it. Underneath the Antarctic and Greenland ice sheet, that is a source of heat that has a 2 to 4 kilometre blanket of ice over the top of it. It raises the temperature of the bottom layers of the ice to melting point, and that's what produces the water that allows the ice sheet to flow. So
it's correct. It's correct. At the planetary level, you can ignore it.
You can.
But actually, it's the single thing that will determine whether I find my million-year-old ice or not, because that will determine whether my million-year-old ice has been melted off or not. So.
Yes.
When you want to drill down for a million years, can you use your 800,000-year borehole?
We can't, because that's that particular place, that's the oldest ice there is. It's actually very slightly melting at the bottom there, and 800,000 is the oldest there is at that site. So what we actually need to find is somewhere probably nearby, or nearby one of those places, with either thinner ice, so that there's less heat coming up from the bottom, or a lower geothermal heat flux. But of course, our knowledge of the geothermal heat flux under an ice sheet is close to zero. Most of the maps of it just show a completely flat, constant value, which is completely wrong, but is the best we know about. So we do need to go somewhere else, I'm afraid, and start again. But the advantage is that we can use a rapid method to get some information out of the hole before we do the proper job, and compare it to what we've already got to make sure we do understand the age profile with depth and that we really are getting old ice.
Is that why you stopped at 800,000 years before?
We stopped at 800 because that's the oldest there was at that site. That was, in fact, we only this is a good story for getting money from funding agencies. We promised the funding agency 500,000 years, and we got 800,000. So we're the star turn, because we gave them 60% more than we promised.
it's just managing expectations, though, isn't it?
Yes.
If we continue emitting carbon dioxide and so on, and keep going until whenever we run out and decide to stop, the Earth's temperature will rise, I presume. Does a certain point come where the Earth will digest all of this, and in 10 or 100,000 years we'll return to a more normal sort of cycle of ice ages and so on, or have we done so much damage that we're permanently flipping ourselves into a quite different state?
Well, it might digest us as a species.
Is this me?
I think this is you, Eric. So I can be flippant.
At least, I mean, whether it does depends on knowledge of long-term processes in the ocean carbon cycle that we don't have a lot of evidence about. But nonetheless, the best estimate is that if you get to, say, that say you go to that 2100 where you get the up to 4 degrees rise, the best estimate is that the CO2 will very, very slowly decrease, but some of it will remain in the atmosphere for as long as 100,000 years. So it'll still be 20% higher than present 100,000 years from now. And actually, because the Earth carries on heating, because it's equilibrating between the atmosphere and the ocean, they actually project that the temperature will stay pretty constant over the next 2,000 or 3,000 years after we stop putting CO2 into the atmosphere, just because the CO2 is very slowly decreasing, but the Earth's still warming because of what was already put in. So the short answer to your question, that was the long answer. The short answer is it will stay, at least as far as we can tell, the CO2 will stay in the atmosphere for a long time. Not all of it, but some of it will stay for a long time. And as a result, we'll miss the next time when we might have gone into an ice age. And then the next one after that is very weak, so we wouldn't have done anyway. So it probably means that we've delayed the ice age cycles by at least 100,000 years. So this interglacial that would normally be 10 to 30,000 years will be at least 100,000.
If I can just, while we're on that topic, you explained very eloquently how come we get the oscillation, what triggers the onset and what triggers us coming out of it. But I'm always perplexed to understand why the amplitudes and the periods are so great, and is some sort of hysteresis effect, presumably. But what is it that causes these things? Why don't we just get small wobbles instead of great big long-term fluctuations?
Well, so it's a difficult question to answer because it is still a research question to which there isn't a clear answer. But, so the textbook answer to what you're asking is that it's all paced by these Milankovitch cycles, which is the cycles of Earth's orbit around the Sun, of which the strongest frequency is 20,000 years, which is precession. I could explain it, but perhaps now's not the moment to explain it. But actually, we see the ice ages every 100,000 years. So the question is, why isn't it every 20,000 years? And that's probably something to do with the timescale of ice sheets growing and shrinking. That it's actually, if you try to grow a big ice sheet, you actually can't grow it big enough to get rid of it again, because you actually need to get it to low latitude to start to get rid of it again. You can't grow it big enough in 20,000 years.
Good answer. I like that. Thank you very much.
I know it was something totally basic. I don't understand why sea level rise isn't uniform.
Okay. Well, let's think about the Mediterranean, or actually one of which is connected to the global ocean. So it's not like the Black Sea, which is completely disconnected from global ocean. But if we raise temperature over the Mediterranean, we'll actually cause higher evaporation. The higher evaporation means that you end up with a salty surface water, which is actually quite heavy. So you can end up with the Mediterranean actually being quite heavy water compared to the water out in the Atlantic, and slowing the inflow down. So you could actually create a regional different sea level change in the Mediterranean just by raising the temperature over the Mediterranean. Locally, for instance, the Thames estuary, the land under the Thames estuary is actually sinking at about 2 millimetres a year. The reason for that is that in Scotland, 10 to 20,000 years, there was a lot of ice, which depressed the Scottish crust. And as the ice has been removed, the Scottish crust is lifting up. There's a bit of a seesaw going on, which means that London is actually sinking towards the centre of the Earth at about 2 millimetres a year. So the relative sea level that we feel is increased by 2 millimetres a year.
The chart you showed, there seemed a big difference between the middle of the Pacific and the
Yeah.
the east of Japan.
Yeah.
And there's not much land there.
No, you're absolutely right. And that part is about atmospheric pressure, which can depress the sea surface, changing in a climatological way. And that record that I showed you was actually over a rather short period, when those climatological, or weather patterns, let's say, rather than climate patterns, were actually in one state rather than the other state. and seem to show that. So that pattern of sea level rise isn't going to persist forever. It's actually more like it's the weather again, rather than the overall climate, which is the global sea level change. But there's lots of factors that make regional sea level different from global sea level.
From the British Antarctic Survey, are there other Antarctic surveys?
Indeed.
And you come up with the same answers?
Generally speaking, yes. Antarctica is a great place to work as a scientist because there are no ownership issues. It's run by an international treaty that most of the nations in the world have signed, and we've said we will cooperate as scientists, we will share data, we will allow inspection of our stations by any country that cares to come and look at them. So it's actually a very cooperative place to work, and if I compare it to the Arctic, where almost none of those things can be said, and actually working with some of the Arctic countries is actually pretty difficult. Getting data and samples out of, for instance, Russia is actually the Russian Arctic is actually very difficult. So, yeah, it's one of the reasons why I love working in Antarctica. But yes, there are active polar research national programs in Norway, France, Russia, US, Canada. They're all in there.
And I should have said that 800,000-year-old ice core was actually a European project, so there were 10 countries involved. It wasn't just us. I happened to be the science leader at the time, but there were 10 countries involved.
Do you know, David, roughly in terms of the total budget on polar research, Arctic, Antarctic, what proportion of that does Britain contribute? Are we punching as well above our weight as we'd hope?
Yes, we are punching above our weight. I do know these numbers. They're engraved on my heart. The UK spends around £44 million a year on Antarctic research.
So a day's operation of the Great Hadron Collider, isn't it?
Something like that, yes, indeed, indeed. Astronomy seems to be very, very good at getting money compared to some of the other subjects. The US actually spends about 10 times that amount on polar research. They publish about twice as many papers as we do, so hopefully, that we're good value for money.
Great, thanks. Yes.
Yes, the risk of coastal flooding depends on the mean level, but also, of course, on any changes or trends in the storminess.
Indeed.
Do you have any news on that?
Yeah. I ran a big European program that was trying to really look at not just sea level rise but changes in flood risk. What we found was that for the southern ports of the North Sea, Sheerness, Edgeberg in Denmark, there is a likelihood that over the period to 2100, as much uncertainty is in that change in the storminess, changes in the size and periodicity of those storm surges, as is in the global sea level rise. So yes, if I was to say that the risk at that one site was totally about sea level rise, I would be leading you astray, because it is also about the meteorology that's driving those storm surges and building them up across the North Atlantic.
And what is the news on that?
Well, the Met Office projections would suggest that over by 2100, the height of the 1 in 50 year storm surge could increase by about 30 centimetres. There's a lot of uncertainty around that, but that's the mid-range number.
What about the frequency of the 1 in 50 year storm surge?
Well, no, that's where the definition that's where the definition of the 1 in 50. I can either tell you how frequently.
Yes, the frequency of a given size or the magnitude of a given frequency.
You've got it, absolutely.
Yes.
But I should just say that David just hinted at the dirty secret of climate modelling there, in a way, which is that predicting what's going to happen to something like storminess in a little island off the coast on the coast of the Atlantic is incredibly difficult, and frankly is almost meaningless at the moment, if I can say so. I mean, it's in most last generation climate models, Britain was about 5 grid boxes. So if you ask me the difference between Norwich and Cambridge, I couldn't tell you, because they're in the same grid box. So it's just really difficult to do, and ministers are always asking for it, and they get answers, and that makes them happy, but they're probably not the right answers.
And the same is true about actually a lot of the climate parameters that we actually critically feel. When we talk about global temperature, or for a region annual temperature, but that's not annual rainfall, and it's not the seasonal rainfall. We'd like projections of how summer rain is going to change versus winter rain. Summer rain just causes us flooding problems and runs off into the oceans. It's only winter rain that fills our reservoirs. So there's a big difference whether the changes that we feel are in the summer and the winter, in rainfall or temperature. It's very difficult.
Maybe make this the last, because I know we were billed to finish at 8 and people may be wanting to get away, but then there may be an opportunity for others to come up and ask in person.
I just wanted to ask which newspaper buy.
I thought that one had gone away.
Well, I will answer that, and the answer is none of them. Because can you imagine trying to encapsulate the complexities of what we've heard in not even a soundbite, a banner headline? There is none. And so anything that's trying to sell newspapers by simplifying this to a banner headline has got to be kidding. Now, is that a fair answer?
That's a very fair answer, and it's actually, that's actually the reason why I think Eric and I are very happy to take time out and come and talk to people, so that you don't actually just have to take the headlines as gospel, and you can, interrogate us a little, and hear where the uncertainties really lie. So,
but you did refer to a region of Antarctica where it wasn't news to you that there's a region of Antarctica where the ice is piling up. That was, it's maybe not the hottest news story on the press. No.
So the answer is that each one has a small bit of the story.
Well, I mean, to be entirely serious about this point, the newspapers talking, especially as they relate to climate change, now are not reporting the normal estimates, the central estimates anymore, because those are not news. They are picking, rather, in this case, diametrically opposite the high estimate and the low estimate. And yes, within the scientific community, both of those ends of the spectrum exist out there, but we're very, very aware of what the mid-range is and what some unexpectedly high is and what something unexpectedly low is. And those are the ones that actually crop up in the newspapers more often than the central estimates now.
I think just to try and be fair to journalists, some of them, there are science journalists, there are still a few science journalists, not very many. Some of them do try and understand what's going on, and of course their editor insists that they write a story that's a bit more sensationalist than probably we would like, but they try and understand what's going on. But clearly there are some newspapers that have an agenda. Unfortunately, the two you mentioned both have an agenda. And so you do have to read some of the stories knowing what the agenda is.
We'll tell you who our favourite journalists are offline.
Well, can I, on all your behalves, and certainly in terms of my own appreciation, thank you both very, very much indeed for giving up the time and for addressing us so clearly and so eloquently and giving us lots of information and a much better perspective within which to read the Daily Mail tomorrow morning. Should any of us wish to do so.
Thank you.
Thank you very much.